Greetings, everybody. This is Mr. Beckstrom again, and today we're going to be talking about Chapter 6, Section 4, the normal distribution. Now, let me kind of start off with this section saying that the normal distribution is, it can be a pretty complicated concept, so it would really help after you watch this video to really read again through that chapter and try to understand it. It's something that appears in statistics very often, and they talk about it in this class. And once again, make sure you read the section and you do the homework on these as well. All right. So what is the normal distribution? Well, it's the most common distribution in statistics, and it describes many real-life data sets. Common data sets which follow a normal distribution include like SAT scores, heights of women, IQ scores, and there's many other things. And the idea of it is that, let's say you have a test score and the average score was 75. In a normal distribution, that 75 would be the most common score amongst all the scores. So if we were to curve it, since it's the most common, it would be the highest on that curve. And then as we look at other scores, so for example, we look at how many 65s or 85s we got, we'd expect to see a lower amount of those. And it keeps getting lower and lower the farther to the left or the farther to the right that you get, making a curve that looks like this right here, where this will be your most common or your average score or data. And as you go to the left or to the right, the number of those scores will start to diminish until you get way down here where there's only a couple of people that got a 99 or 100, and way down here where there's only a couple of people that failed it. Alright, so what are some properties of a normal distribution? Well, like we just kind of explained, it's a normal curve that's bell-shaped. The highest point on the curve is the mean of the distribution. Remember, the mean is the average, so that would be whatever the average of your data set is. The mean, the median, and the mode, all three of those statistics that we just looked at are all the same. So they're all at the center of that distribution curve, normal distribution curve. The curve is symmetric with respect to the mean, so the area to the right of the mean is going to be the same as the area to the left for similar distances. The total area under the curve is 1. We use an area of 1 so we can correspond that to probability. So when we say that there's an area of 0.75, that would mean that there would be a probability of 75%. Kind of erase this. Roughly 68% of the data values lie within one standard deviation of the mean. That's both to the left and right. 95% of the values are within 2 standard deviations, and 99.7% of the data values are within 3. So going back to that test score there, looking at this normal distribution, each one of these is a standard deviation. So this is 1 standard deviation to the right, this is 2 standard deviations to the right, this is 1 to the left, this is 2 to the left. So these percentages, which are the area under that curve, also correspond to the number of data values that are also in that area. So let's say, for example, I had that test score with a mean of 75 and a standard deviation of 15. That means that 1 standard deviation would be 15 added to that 75, which would be 90, and 1 standard deviation to the left would be that 75 minus the 15, which would be 60. So we would say that approximately 68% of that data lied within 1 standard deviation of the mean, or between the scores of 60 and 90. Alright, so let's talk a little bit about the z-score. The z-score is the scores on the bottom of that curve that correspond to the number of standard deviations. So a z-score of a +1 would be 1 standard deviation to the right. A z-score of a -2 would be 2 standard deviations to the left. And if we're given a data set with a mean and a standard deviation, we have this formula here to calculate the z-score. The x is whatever data value we have. The mu, looks like a u, is the mean, and the lowercase sigma is the standard deviation. Alright, and we can calculate the area under that curve, which, remember, is the same as the probability of whatever we're looking at, by using table 6.6 on page 436. Now, I will say there are different tables calculated different ways. A very common way to do it in statistics is to have a table that shows you the area under the curve from that z-score to the left. Some may do it from the z-score to the right. This table here actually calculates the area under the curve from the mean to the right. So if you're given a z-score of a 1, it will calculate that area under the curve. Go back up here from 0 to 1. It'll be this area right here. If we were given -1, we don't have that on that table. However, since we know it's symmetric, the area from 0 to -1 is going to be the same as the area from 0 to 1. You can see these areas both look the same, and in fact they are. So whenever they ask for a negative z-score, we're just going to use the positive equivalent of it. And it always starts right in the middle of the graph at our mean. Alright, and let's go to a couple of examples here. Example 1. Suppose the distribution of 2,000 SAT scores follows a normal distribution with a mean of 975 and a standard deviation, excuse me, let me correct that, and a standard deviation of 75. Now, what that means is, first of all, it says it follows a normal distribution. That's important because now we know that it has all those properties of a normal distribution that we had talked about earlier, which means that the scores are symmetric per the mean, and it has all those other qualities that we use in statistics to look at. So, a mean of 975 and a standard deviation of 75. How many scores do we expect to fall between 900 and 1050? How many scores do we expect to fall above 975? So 2 questions here. So the first one, how many scores fall between 900 and 1050? I'm going to use this right here. Since our mean is 975 and our standard deviation is 75, I notice that 975 minus 1 standard deviation gives us the 900 that we were asked in the problem. Therefore, we're looking at this area right here, between 0 and -1. And the same thing, we're also looking for this area too here, between 0 and +1, because 975 plus 75 is equal to 1050. So we're breaking this problem up into 2 different parts. So we're going to be, since the table goes from 0 to some z-score, we're going to look at this value here, and really we could either just double that value there, we could either just double that value there, or we could find each of them separately using the fact that the curve is symmetric and the negative z-scores will have the same area under the curve as the positive z-scores. So looking at the percentages, 34%, 34%, add them up, we get 68%. So about 68% of the scores are going to lie between 1 standard deviation of the mean, or between 900 and 1050. Next question is, how many scores fall above the 975? Well, if this is our curve and the mean is right at 970, the mean is right at 975, we know that half the curve lies to the right and half the curve lies to the left. If you look at the table, you'll notice that the areas go all the way up to 0.5, and that's 50% or half of the curve here. So the answer to that question is just 50% or 0.50. All right. Example number 2. Using table 6.6, find the percentage of data that lies in the region between z equals negative 2.1 and z equals 1.3 for normal standard distribution. So we're looking from this area, from negative 2.1, which is going to be on the left side of the mean, all the way over to 1.3, which is going to be on the right side of the mean. Well, remember, our table isn't going to be able to give us this entire area at once. We're going to have to break this up using this mean here. So if we look at this portion here, we can just find from 0 to 1.3 using our table. We just look at 1.3 and we'll get an associated area of 0.403. So that's 40.3%. Now the other area here from 0 to negative 2.1, we're going to use the fact that that area is going to be the same as from 0 to positive 2.1. So we're going to look up positive 2.1 on our table, and we're going to get 0.482. So the area under the curve from negative 2.1 to 0 is 0.482, and from 0 to 1.3 is 0.403. We add those two areas up, and we get a total of 0.885, or about 88.5% of the data would lie within those two scores. All right, and the last question is, suppose that you apply to Harvard and they only accept the top 1% of SAT scores. So let's say we're using the previous values of the mean of 975 with a standard distribution of 75. What score would you need to be considered by Harvard? So first of all, these 975 and 75 scores are not necessarily accurate. If you want to look up those scores, sure, it's depending on the time period, but using these scores to calculate that, how would you do that? All right, well, first you need to find the z-score that corresponds to the 99th percentile. That means we need 99% of the area under this curve to be shaded, and we're just looking at that z-score that corresponds to a little tiny area to the right that's just going to be the 1%. Now, since we know our table goes from the mean out to the right, we know that we're looking for 49% because the total right-hand side of that from the mean is going to be 50%. So if we looked at 0.49 on our table, that would leave a tail of 0.01 to the right of that, on the right side of that tail. So what we do is we go to our table and we look up 0.49, and you're going to get a set of z-scores between, I believe, 2.31 and 2.34. You can use any of those that you want to. All of those correspond to 0.49. So I just picked 2.32 here, and now we want to find out what test score corresponds to 2.32 standard deviation to the right of our mean. So we go back to our z-score formula. This time we know the z-score, and we're trying to find the actual data value, which is our test score. We plug it in, we multiply both sides by 75 to get this out of the denominator, and then you're going to add 975 to both sides, and you're going to get a test score of 1,149. So that means that that's the test that starts the top 1% of all test grades. Therefore, you'll need a score of at least 1149 to be in the top 1% and to be considered by Harvard. Alright, so once again, take a look through the chapter, see if you can read a little bit more. Wikipedia is a good source for kind of seeing some more information about the normal standard distribution. And if you have any questions, please give me a call or send me an email, or we can set up an appointment. And thank you and have a great day.